Yeah. Afternoon, everyone. Let's get cracking. Before I get into today's lesson, I sent you some information yesterday. I trust you have looked at it. If you have any queries, I am open to treating with that now. I also sent you the information regarding your project. Again, if you have concerns, this is the time to raise them.
Yes, sir. Good evening.
Afternoon.
Regarding the project, sir, I'm seeing a due date, but have you given the project as yet?
Okay. So that is suggesting that you haven't looked at the page, right? That hasn't been uploaded to you?
No, sir.
No, sir.
Serious?
Yes, sir. So we're a bit confused.
That is serious. That's a serious matter. All right. Okay. That was.
So that's why the due date seemed a bit close.
In the message I sent you, right? Did I make reference to the message I sent?
Yes, sir. Regarding the due date, but there's no uploaded product.
Man, that's a major oversight. Yesterday was a little crazy, so anything is possible. All right. Let's see now. Where are we? Networks 2. Oh, all you got were the tutorial questions. I'm assuming you saw that.
Yes, sir.
Okay, so problem addressed. Project is now posted. So that it's right below tutorial questions. Okay, that was a major oversight on my part. All right. Okay, so we have addressed the first one. Next.
Sir, does that mean that the date seen that we're seeing the project?
No.
Is going to be no.
You have been given 4 weeks to complete this. Is that an activity that if you're on top of your game can take you 1 evening? You have 4 weeks. I think that's reasonable. All right, so you have the questions. I'm assuming you have looked at them. So let us let's go through them. So I'll just get some support here. Let's start with Mr. Sawyers. You're right up top, Adrian. So the circuit is before you. It says that the circuit shown below is at steady state at t equals 0 minus. Determine the voltage across 24 ohm resistor in 600 microseconds. What's your approach, Mr. Sawyers?
Sir, the first thing I would do is I would find the instantaneous current in the circuit.
Okay. In the circuit. All right, cool. When you say in the circuit, you mean in all the branches?
Yes, sir.
All right. And having done that, next step. Having done that, Mr. Sayers, what next?
I would find the equivalent resistance seen by the inductor.
Okay. Continue.
Then I would calculate tau and use that to find the voltage across the 24-ohm resistor.
All right, so you opted first to find the current through all the branches. Is that necessary? Just us?
I'm not sure. When I looked at the circuit, that's the first thing that came to me.
All right, and that is how I don't want you to approach any question in networks. It can't be, what came to you, the first thing that came to you. You have to be a little more methodical than that. So below you have Mr. Blackwood, or above you have Mr. Blackwood. Mr. Blackwood, let me hear your approach. Blackwood?
Yes, sir. I'm just joining in.
Therefore, I want to hear your approach to solving the question, the problem.
Well, I didn't really go through the question, sir.
Okay.
I was
Hanson? Hanson?
Oh, yes, sir. I heard Thompson, sir. All right. So what's the question, sir?
Oh, this is getting worse.
No, no. What I'm asking is, what do you want of me now? What do you want?
I need your approach to solving the problem before us.
Oh, the first thing I would do, the fact that it says it's at steady state, you know that the inductor going to be short circuited.
Represented by a short circuit. We're not short circuiting the inductor. I've been correcting you guys long enough. But carry on.
Yes, so that's what I did. Represent the inductor by a short circuit. So what I had done now is, well, the first things first, I found the resistance, the total resistance.
From the perspective of?
Looking through the short circuit, looking through the branch with the short circuit.
Okay, go on. I hear you.
All right, so after that, no, sir. What I did, I found the total resistance, and then after that, no, sir, I found the REQ.
Okay, so REQ is from the perspective of the inductor.
Yes, sir, yes.
All right, so the total resistance before would have been from the perspective of the source, the 60-volt source.
Oh, yes, sir.
That's why okay, carry on.
All right, so after that, no, I found the total resistance, and I found REQ, and then after that, I found IL, the current across the load.
Through
the load. Yes, sir.
Okay.
And then you use that, and then afterwards you find tau, use the inductor value and the resistor value to find tau.
Thank you very much, Miss Hanson. Your effort does reflect the grades that you have been getting, which is pretty good. Thank you. So let's look back at the question. So, as Miss Hanson correctly pointed out, we first need to know, because we are going to be opening the switch. Yes, because we're going to be opening the switch. And we're already told that the circuit was in steady state at t equals 0 minus, meaning it's in steady state just before we open the switch. then it means that our inductor is going to be represented by a short circuit. So what I want to determine is what is the current at steady state. So we know that I0 minus is equal to I0 plus, and this is going to be the initial current through the inductor. Good. So in finding I0, yes, RT, from the perspective of the 60 volt source, let's see now. Mr. Parker?
Yes, sir.
Let's give me the equation for RT.
7 plus bracket 24 parallel bracket 8 plus bracket 6 parallel 12.
Thank you, Mr. Parker. All right. I don't think we need to spend much time looking at this type of thing. So what's the total resistance here?
$15, sir.
15 ohms, sir.
15 ohms. Okay, which means that IT is equal to 60 over 15, giving us 4 amperes. Good. So we have 4 amperes. And what we're interested in is the current through the inductor. Yes? So what's the current through the inductor branch? Well, we're using current division. So let me just put, let's call this I1, and then we call that I2. So I1, is that equal to? That's the current through the 8, flowing towards the 8 ohm. What are we dividing? That's 24 in parallel with what?
12, sir.
12.
Parallel 12. So I1 is equal to?
Need over 3, sir.
Yes, sir. It's over 3.
It's 24 IT over 12 plus 24.
24.
Okay? So that gives us 8 over 3, or 2/3 the total. Good? Which implies also that I2 would be equal to, I2 is a current through 6 ohm. What's I2?
1.778
12.
amps.
12 over 6 plus 12 times 8 over 3.
So it's again multiplied by 2/3, so we get 16 over 9 amperes. All right. So the current through the inductor is 16 over 9. This implies that I0 is equal to 16 over 9 amperes. Okay, so now that we have the initial current, we want our equivalent. So the switch is now open. The switch is open, and we want the resistance looking from the inductor. So let's see now. Mr. Dixon?
Yes, sir.
Equation for REQ.
Equation for REQ. All right, give me a second.
All right, we're going to move on. We're doing a second. Mr. Beckford, equation for R equivalent.
6 plus bracket 12 in parallel bracket 8 plus 24.
Thank you. All right. What's that equal to?
162 over 11.
It's 162 over 11 volts. Okay. So we now have the equivalent resistance. Let's see, So Morrison?
Yes, sir.
Give me the general formula for the current. The general formula for the current from the inductor.
It would be I equal current e to the minus
Current, which current?
initial current.
And how do we represent that?
I0 plus I0 e to the minus 1 over T over L over R.
Okay, so what's the give me the single fraction?
That would be RT over L.
Okay, so now that we have that, just give me the values to plug in, please.
That would be 1.778.
What and if decimals just now we have I0 at 16 over 9.
16 over 9, yes. This 16 over 9 times e to the minus 33 over 162.
RT, what is R?
R is 14.73, sir, the equivalent.
R is right here. It is 162 over 11.
Fractions, oh yeah. 162 over 11 times.
That's T, and we're dividing that by?
The inductor value, 3 times 10 to the minus 3.
Okay, so give me let's simplify all of that for me now.
So that would be 33 over 162 milliseconds. 16 over 9 e to the 33 e to the minus 33 over 162.
So 33 must be in the denominator, sir.
Yeah, yes, sir. Yes, sir. Yeah, thanks, sir. Yeah. 33, 162 over 33.
It's 3 millihenries.
Yes, sir.
Yeah, so what should be in the numerator?
3 times 10 to the minus 3.
Okay, so now we have I. All right, thank you, Mr. Morris.
Okay.
Now we have I. So Stuart,
Yes, sir.
What we're interested in is the voltage across the 24 ohm resistor. So what do I do with this?
With that, sir, you now use, first, sir, we'll have to find the exact current, sir, which would mean that we now put in the 600 microseconds for the T. And then after you find that value, sir, we use current divider to find the current to the 24 ohms.
Okay. All right, fair enough. Sir Thompson, do you have an alternative approach?
Me, sir, that's, sir.
We don't have any other Thompsons here.
Sir, that's the approach I attempted, sir.
Okay. All right. So using current divider, we find I24, which is 12 times 16 over 9, e to the minus 162 t over 33. Okay, and we're dividing that by 12 plus 32. All right. Are you okay with that?
I need you to take one picture of me.
Yes, sir.
Yes, sir. Yes, sir.
Okay.
Yeah,
We have here, where am I? So from 4, 3, so we get 4, 3,
What?
4,
Right now.
get 11,
Okay.
16 over 33. E to the minus 162
I just do it right
over 30.
Why?
Mr. Haynes?
6 hours is supposed to
Mr. Haynes, please mute your mic.
an immaculate thing. The issues are supposed to heal?
All right. So with that being I24, it means that V24 would be equal to 24 times 16 over 33, e to the minus 162. All right. At t equals 600 microseconds, calculate V24 for me, please.
Sir, 0.614 amp.
I got 11.636 volts.
Thank you, Mr. Richards. 11.636, you said? Mr. Richards? Thank you. Volts, because we're calculating voltage. So that amp response I got would have obviously been incorrect. All right, so that's the solution to question number 1. Do you have any questions?
So initially when the statement said the circuit was in steady state at t equals 0 minus, wouldn't it mean then that the 12 ohm would have been short circuited by the inductor at that point?
So if I put a short circuit here, what's the implication now? What's the question?
I was saying if it was short circuit, the 12 ohm and the as parallel to the.
Why would it?
Just because the short circuit, I was just thinking that. But
is this a short circuit?
no, sir.
It's a connecting wire. It's a short circuit.
Okay.
If I were to open these 2 points and then I connect them by a wire, am I not short circuiting the path?
Yes.
Okay, so why wouldn't the 24, why wouldn't that branch short circuit the 8 and the 6?
Get it now.
Okay. All right. And any other questions? All right, question number 2. Where was I on my list? Ms. Brown? Brown? Can you speak up, please? I can hardly hear you.
Are you hearing me?
Okay. So for question number 2, circuit is in steady state. We want the voltage V, which is the voltage across the 18 ohm, when the switch is open. Let me hear the approach that needs to be taken here, or that you would take. Ms. Brown? Sayings? Javon?
Yes, sir.
Let me hear your approach here.
I didn't quite get to that question as yet, sir.
Okay. Cameron?
Yes, sir.
Let me hear the approach you take here.
All right, sir. I never reached that question, sir, but I was trying to attempt it. All right. You would it would be the same approach like the first one, sir, except that you would open the capacitor.
Oh yeah, I'm listening. Carry on.
I must carry on. Okay. So, sir, after you open the capacitor, so you're going to find the REQ.
All right. Okay. What do you mean by REQ?
The resistor, sir, through the circuit, the total resistor. When the capacitor is open,
Okay. All right. Okay, thanks, Ms. Cameron. Mr. Calhoun?
Okay, sir.
No. Calhoun?
Yes, sir, here.
Yes, let me hear your approach to this.
We never get to attempt it fully, but I guess it's
Okay.
similar to the first.
Okay. Thank you. So Black?
Afternoon, sir. You hear me clearly?
Yeah, man. Hearing you loud and clear.
Okay, so the approach that I would take to this, I'm seeing that it says the circuit is, the switch is open after being in steady state. I mean, T0 minus before opening would mean that the capacitor is fully charged, and therefore, in effect, in the circuit, it will be represented by a short circuit.
Yeah.
Yeah. So knowing that, from the perspective
Represented
of the source,
by what?
an open circuit. Right.
Okay.
Yeah. So knowing that, we'd find the total resistance from the perspective of the source, and then we use that to find the initial current, and then find the current in the branch where the open circuit would be. No, not the current in that branch. But since the open circuited branch would be in parallel with the 12 ohm resistor, we could find the voltage across the 12 ohm resistor, and that would give us the same voltage that the 6 ohm resistor would be in.
All right. Okay. Thanks. So, Hodges, you have anything you want to add? Karen?
Yes, sir. Here.
Karen, sorry.
Kiran, sorry. All right.
Karen. Wrong. I tried it twice and get it wrong, but carry on.
Hodges then.
Go ahead.
So, what he said is correct so far. You'd want to, after you find the RT, when you represent the capacitor as an open circuit, then you'd want to find the voltage across the 12, and that would be the VO4.
Oh, why are you guys so interested in the 12 volt?
Or the voltage across the 6. Sorry.
No, hold on. Listen to the question. Why are you all interested in the 12 volt? Look at the question. What are you asking for?
The voltage across the 18 ohm.
So the 12 ohm, why are you interested in it?
Okay. I see what I said.
No, I didn't say you're wrong, and I'm asking you, why are you so interested in it? Well, the fact that I asked the question don't mean that you are incorrect. You know?
Because that would represent as the initial voltage, VO. Okay. That would be because the voltage across that branch with the 15 micro, with the capacitance, is the same voltage across the 12 ohm.
So what are you really finding? When you find that voltage, what are you really finding?
The voltage that the capacitor is supplying the circuit with after it is closed. It is closed or open, yeah.
Is that what you're really finding, no? Is that what you're really finding?
Parallel branches voltage.
Huh? I'm sorry, is that what you're really finding? Or is it that they're finding V0?
V0 is the initial.
Yeah, it's just that the thing's simple, man. It's all theory we're talking about, you know. So let's go then. From the perspective of the 80 volt source. Yes, that's before the switch is opened. What is RT? Morgan? Morgan? So Morgan?
Yes, sir.
What's RT equal to? That's before we open the switch. Give me this.
RT before we open the switch. Before the switch opens, sir.
Yes. What's the resistance? Come on, Mr. Morgan, man. It's only today we have, you know. All right. Samash, help us out. What's RT? Just give me the expression.
Expression would be 18 in parallel with 8 plus 12, close bracket, in series with the 10.
All right, so we could start from the front of myself because I was wondering why you got an 18.
All right, sir. So the 10 is in series with the rest of the circuit, which is 18 in parallel with the rest of the circuit, which is the 8 in series with the 12. And that equals to 370 over 19 ohms.
370?
Yes, sir, over 19 ohms.
Okay, I'll take your word for it.
No problem, sir. Anything else, sir? That's correct. That's correct.
All right. So continue so much. Now that we have RT, we want to find V0. So that's V0.
All right. So to find V0, sir, we would have to use voltage divider.
Okay.
So the voltage will split between the 10 and the rest of the circuit.
So what you want, the rest of the circuit would be from here on, right?
Yes, sir. And that part will be equal to 180 over 19.
Okay, so you want V, and of course, because of how the circuit is arranged, the rest of the circuit, the voltage across the rest of the circuit would also be equal to V18.
Indeed.
Look at your formula. 18 is in.
Yes, sir.
So it's really across the 18 ohm, huh?
Yes, sir.
Okay. So V18, carry on so much. So it's between 10 and the 180.
So that's you want to complete the final answer, sir, or you want the expression same way?
I'll give you the expression, man, so everybody can know why we do what we do.
All right, so we have 180 upon 19 divided by the 10 plus the 180 upon 19.
180.
Yes, sir.
And that's times 80, right?
Yes, sir.
Over 180 over 19 plus 8.
10.
All right.
Plus 10.
Okay, sorry.
Plus 10.
10.
Okay.
Yep. Tell you what, let's go to decimals now. I'm tired of the fraction.
All right. And that is equal to minus. Oh, you're on fraction now, sir?
Go ahead. No, give me the decimal. Minus what?
Minus 38.919 or minus 38.9189.
All right. So, Mr. Marsh,
yes, sir.
Explain to me why you throw this minus into the mix.
All right, sir. Go back to the circuit, sir, please. Sir, if you realize, sir, we're moving from the negative terminal of the source rather than the opposite direction.
Okay. All right.
Okay.
Well, yes, but also the V that we are looking at. Yes, the positive is up at the top, eh?
Oh, yes. Sir.
So that's the real key. Because if I didn't give you the polarity, any other polarities of V, then you could stick with the positive. Or if I had put the plus for the V down here, then you could have maintained the positive. All right, so
yes.
Okay, so that's V18, but we want V0, which is equal to V12.
Yes, sir.
Okay. And that's going to be equal to 38.92 times 12 over 12 plus 8, right?
Yes, sir.
Which gives us
minus 23.35 volts.
Thank you, sir.
You're welcome, sir.
All right. So next in line, the smart beam. Now that we have V0, we want to find REQ looking from the capacitor. So what's the equivalent resistance? Now that we have opened the switch, what's REQ?
Sir, if we're looking from the capacitance, it's going to be the 12 in series with the 8, which is in.
Remember, we're looking from the capacitor. So the capacitor is now viewed as the source.
Oh, I was looking at it when it's open circuit. It's going to be 6 in series with the rest of the circuits, which is going to be bracket.
Go ahead.
12 parallel with the rest of the circuits. 8 in series with the 18, yes.
You're welcome.
Thank you, sir.
What is that equal to?
Sir, give me a second.
Does anybody else work it out?
Yes, sir.
Yes, sir.
What is it?
170 over 19.
13.21 ohms. All right. So we now have REQ and RC is therefore equal to that's RC.
14.1 times 50 times 10 to the minus 6.
230 microseconds.
All right. So I want now VC. So what is VC? Who else we have on line? McKinnon, what's VC?
VC, when I looked at the circuit, it said determine voltage at T equals 0 when it's just opening. So I took VC to equal V naught. That's what I took it to equal to. I was thinking about
But all this work, then why you think we're doing all this work? If that was VC. I can't be VC.
Okay, well I have it here now worked up both ways, V naught e to the minus T.
If you have it work both ways, that means you're not sure what you're doing. That's it.
Yeah.
So tell me what VC is equal to.
In that case, VC would equal to V naught, which is the minus 23.35 times e to the minus T over tau.
You sound like you're guessing. So Pedro, what's VC?
Yeah, sir.
What's VC? What's your expression for VC?
as you said before, sir, it would be the VO to the exponential of tau over t. You hear me, sir?
Me hear you, but may I ask for VC? I don't want no formula from you. I want VC.
What you want there?
I want. Give me VC. What's VC? Give me the complete expression for VC. Ms. Campbell, what's VC? Give me the expression for VC based on all that we have done so far. What's VC?
Sir, you know that I did kind of chip out, so I wasn't here for a good part of it.
All right. So let's see who is below you. So Atkins, what's VC?
Minus 23.35 e to the minus t over, sorry, e to the minus 4.694t.
Oh, you have inverted the 230 to the 10 to the minus 6. All right, so the mirror you have?
E to the minus 4.695t.
4.695?
Yes, sir.
So the reciprocal of 213 times 10 to the minus 6 gives you 4 point. That doesn't sound too right to me, unless my maths gone cuckoo.
Minus 4,694.8.
4,000 what?
694.
694.8?
Yes, sir.
So I can see you have to know when something wrong, all right? So that is VC. But what we're interested in is V. So where do we go from there?
The voltage divider.
Use voltage divider.
We use voltage divider between
the 8 and the 18.
And so we apply it between what? Come on, students, we are at these two simple questions for the last 40 minutes.
The 12 ohm and the 26.
12 and the 26. Let's look back at the circuit. This is VC. This is where VC is, right? I will walk the voltage across the 18 ohm. So we apply voltage divider between
6 ohm and
6 ohm, the rest of the circuit.
Yes, sir.
And let's call that V parallel. So what is V18? How do we find V18? How do we find the voltage? Once we have that voltage, what's V18?
Voltage divider again.
V18 go equal V parallel. You're fine. Times the other 18 over the sum of 18 plus 8.
I'm not going to work that out for you. I'll leave that to you. Just to let you all know that this question was taken directly from an exam paper. So you will have a sense, well, all of the questions I give you are from exam papers. All right? So again, we first find V0. Right, so we find V0. From that, we also find the equivalent. So we are able to find VC. And then we find V18 ohm using voltage divider twice. Any questions?
Yes, sir. Just to make sure I'm following. The V18, it's going to be an equation, right? And not just
when you have no value for T, so what you have is an
right.
expression.
Right. Okay.
All right. If I had given you a time, then you would find a final value.
Okay. That was just where I wasn't so clear on that side. Okay.
Okay. All right. Question number 3. I'm getting the impression, based on the responses so far, that some of you at least spend 5 minutes looking at the questions, but quite a few persons sat on their hands and waited for class today. And I know that those in the latter group are not helping themselves. So I don't think I'm going to spend a lot of time going through the next 2. Save and accept. We'll just, look at some basic approaches, and then those who. So during the 1 hour tutorial, I will just make myself available, and those who want to clarify what they have done, I'll respond to them. But I'm not going to sit here and facilitate those who have not even made an attempt at these questions. All right, so let's talk briefly about question number 3. So I have a circuit in figure 2, switch is opened at t equals 0 after being closed for an extended period of time. Calculate the voltage across the 2 ohm resistor for t greater than 0. All right. Rather interesting question. So Mr. Where are we now? We're at Mr. Richards. Remain? Let me hear your approach, huh? Let me hear your approach to this.
The first thing I did was I found the voltage at the first node, right above the switch.
That's right here. Sir Richard, you still there? Romain? All right. Look like we lost. Okay, go ahead.
Using that voltage, I found
Yes,
the current that.
Found the voltage at this point.
Yes, sir.
Okay. All right. Fair enough.
Then I found the voltage flowing, that would be flowing through the
You found the
2
what?
ohm. The current that would be flowing through the 2 ohm resistor.
Okay.
Since that inductor would be represented by a short circuit, that would just be V1 over 2.
Okay.
I then found tau L over 6 ohms plus 2 ohms.
All right, but all right, you're taking me through that process, but based on what we have before us, is there any special condition that is being represented in this circuit? When I open this switch, all right, with the switch in place, with the switch closed, yes? What kind of circuit do we have? Describe the circuit with the switch closed.
Sir, the switch closed over.
Sir Richards, I'm gonna finish with it.
Okay.
Describe it, sir.
Yeah, man, with the switch closed, describe the circuit. Can be anything that you consider special about the circuit. Let's describe it. Let's describe the circuit.
Well, when finding steady state, we would have to.
I didn't ask you about that. I said describe the circuit with the switch closed. Describe the circuit. Tell me some important things about the circuit. It's not a technical question. You know. I said with the switch closed, describe the circuit. Didn't ask you anything about steady state or anything like that. Just describe the circuit before you. All right, let me try Mr. Gill. Tarek, describe the circuit with the switch closed. Just describe the circuit that you have here. Tell me some special things about the circuit.
All right, sir. Starting from the 15-volt source, you have the 6 is in series with the rest of the circuit.
You can't say that, Mr. Gill. It's impossible for you to say that. That is why I start with this simple question. Describe the circuit. There's absolutely no way you can tell me that that 6 ohm is in series with anything.
There are 2 voltages present when the switch is closed.
Thank you very much, Mr. Hodges. So you have a 2-mesh multi-source circuit. That's how you go, Mr. Gill?
Yes, sir.
So if I have a multi-source circuit, yes, what does that tell you immediately in terms of its analysis?
Sir, the traditional in series and parallel won't work. It have to use with a measure.
Thank you very much. So you realize that where you started was incorrect?
Yes, sir.
Beautiful. So, you know, before we get into all the fancy stuff, we have to go back to the basics. And the basic says, with the switch closed, I have a 2-mesh, 2-source circuit, which means that in starting the circuit, I have to consider using mesh analysis, nodal analysis, superposition, something like that. We understand this now? So the question is, which one you want to start with? Oh, no, before I go there. When I open the circuit, what would have changed? When I open the switch, what would have changed? So I have removed the 5 volts, but what would be the impact of removing one source? If I remove one of the sources, what would be the impact?
Then you could just use series parallel and those stuff to calculate it.
That's the approach, but what's the impact? In other words, what kind of response would I now experience based on the theory that we have? Go again?
Forced response.
Forced response. Because I now have a different source driving the inductor. Before this, I had these two sources. Once I remove one of them, I will now have a different source. So it means that I'll have to find the two steady states. That's right, go? So before we put pen to paper, it's important that we look at the circuit, make sure we understand what it is that we really want to find. So we're trying to find the voltage across the 2 ohm resistor. But of course, if I know the current through the inductor, I immediately know the current through the 2 ohm, right? Right with me?
Yes, sir. Yes, sir.
So and we know that the voltage across an inductor, you're going to have to differentiate the current. So rather than working it from a voltage standpoint, it will be easier to work it from a current standpoint. So if I have the current through the inductor, I immediately know the current through the resistor, which is why I said, Mr. Richards, which is why I pressed you, Mr. Richards, because you started talking about voltage. And the fact that you started talking about voltage, I realized that you had not thought through the problem.
I use nodal at first, sir.
I know that you use, but the fact that you're talking about voltage, that's the point I'm making. The fact that you start by referencing a voltage means that you have not thought through the problem. Because if you have the voltage, it means for you to get the voltage across this, across the resistor, you would also have to find the voltage across the inductor. What's that go? Sorry, Chats?
Sir.
And how would you find the voltage across the inductor?
LDID.
Huh?
LDI over DT.
Exactly. So it means, therefore, that for you to find the voltage across the inductor, you'd still have to find the current expression. That's right, Gossa?
Yes, sir.
And if you have the current through the inductor, then what's the point in finding the voltage? Because you immediately would know the current through the 2 ohm resistor.
Fair enough, sir.
Oh, you understand why I say you have not thought, you didn't think it through?
Yes, sir.
Okay, sir. It's not a criticism, you know, Mr. Richards. Nothing to defend, nothing to defend. We are all here to learn. So, I'm going to ask you, Mr. Gill. What approach then would you take?
Sir, I would try the mesh analysis.
Okay, so if we do mesh analysis, that's mesh 1, that's mesh 2. Remember what we are trying to find here would be the, since it's at 0 minus, or it was closed for an extended period, it means that we are trying to find the first steady state.
Yes, sir.
All right, and that would represent what? Well, it don't really represent anything. Would represent, yeah, what would that represent?
So that would represent the initial current flowing through the inductor.
Remember we went through the process saying that we're dealing with forced response. That's how it go?
Yes, sir.
So what would that represent? What would you use that to represent or to calculate?
Sir, would use it as I0, sir.
All right. Okay. we'll use it to find A. That's where I was going. Remember, we have A e to the minus t over tau plus B. You remember that expression for force response?
Yes, sir.
Doesn't change. Same expression we have to use now.
In the initial conditions and
exactly
the new initial conditions.
So Mr. Gear, we're doing mesh analysis. Just look at it. Remember now, this is represented by a short circuit at steady state. Yes? So quickly, you're on top of your game now. Just give me the matrix for this.
So that would be 6 plus 3 would be 9 for A. Yes, and then you have minus 3 and minus 3 by, yes, and then you have 3 plus 2, which is 5, and that would be I1, I2 equal to, that would be, that is 15 volts. 15, yeah, 20. That's a voltage rise. And that where you have minus 5 in this.
And what we are interested in is I2. So quickly, drop that in your calculator and tell me what I2 is equal to.
We're doing 16.67 milliamps.
All right. Now, when I open the switch, oh, all right. After Mr. Williams, Travis.
Yes, sir.
Now, when I open the switch, what do I calculate? The switch is open.
The switch is open, so you would now calculate the current through the R2 resistor at a long period after like time infinity.
Okay, and that is equal to what?
B. No, yeah, B.
All right, so after switch is open, so after opening switch, yes, let's call it IL, what's that equal to? Travis?
Let me just work it out.
Well, look at the circuit. See the circuit there? What is it equal to? The switch is open.
Divided by R. Yeah, 15 divided by 8.
All right, which implies that A is equal to, if you want to call it, I0 minus, or B. What's A equal to?
Negative 1.458.
How you get that? Who gave that answer? Mr. Jones? Who said the 1.458? Continue, Mr. Williams. What is A?
F of t minus b.
F of t minus b, which is, Sarges? Hodges?
Yes, sir. I'm looking at it, sir.
Sir Williams, you open up your mic just now. You want to answer?
Minus 1.458.
Okay, so now that we have A, of course we have B, who is after, you know, Mr. Williams. Bora, what is REQ?
We are still at the switch opening, sir.
But it's only one time we open it. Yes?
Okay. 6 plus 2, which is 8, sir.
You're asking me?
Telling you, sir.
Then tell me, man. Mr. What is REQ?
6 plus 2, 8, sir.
Thank you. So what is tau?
Tau is equal to R over L, which is
R over L,
which is 4.
Sir, is equal to 1/3.
L over R, sir.
L over R, which is 2 over 8, or a quarter. Okay, so what is I equal to now? So what's I equal to? Give me the expression for I.
AE 1 over, so I don't remember the expression, sir.
Where did this thing go? So Paul,
it's B over R.
That is I.
Yes, sir.
What's I?
The I is equal to A, which I think was
All right, give me that first. Give me that first. With A and B.
Okay.
Just give me the expression in terms of A and B. Go ahead.
Oh, A e to the minus t over tau plus B.
All right. So what is A again? So we have A here.
416.
Oh no, this is A. So that's minus 1.458 e to the minus 4t. And what is B?
15 over 8.
15 over 8. And of course, the unit is amps. Now, you can quickly test whether or not your answer is correct. At t equals 0, what would the current be equal to? If we put 0 for t, what will the current be equal to?
A plus B.
I2.
A plus B, which is 15 over 8 minus 1.458, which gives us what?
417 million.
416.67. You know, Mr. Black, I'm going to single you out. I'm going to tell you publicly, right? You have this propensity to chop off decimal places. And I'm telling you publicly, and for those who are here, be warned. I am going to penalize you severely if you continue to do that. I've been warning you from networks 1, and you continue to do it. He who hath an ear, clean it out and listen. All right? Okay, so 416.67. With T at infinite, which is of course the current that we got when in the initial stages. So in other words, at T equals 0, which is before we close the switch, before we open the switch, sorry. Yes? The current through the circuit or through the inductor would have been 416.67 milliamps. Good. When I open the switch, after a long time, which means that T is at infinity, all of that would be 0. So I would be equal to 15/8. Bother with me? So you know that your answer is correct. All right. Any questions? Wow. It take 2 hours doing something that I thought we would have taken 20 minutes. Any questions? Any questions? Now is the time.
No, sir. No.
I thought the only question, Mr. Black. Oh, but Mr. Brian, you come late.
Yes, sir.
I thought Mr. Black could have only asked how much you're going to get docked. But
Wait, sir, aren't you supposed to find
oh, you were supposed to find the voltage. You're right. But once we have the current, we know that V2 ohm.
Yeah, I just
V2 ohm is equal to 2 times I. All right?
Yes, sir. You want the answer for that, or just good?
And then if you look at multiply that, man, then we know.
All right.
We can multiply that. We take the money from you, take and go home. All right. So, final question. I still have some work to do. You know. We're still going to do another lecture. I shouldn't even record this, but anyway. All right. So, we have a series RLC circuit. All right. So, let us see, you know. Let's see the other late comers.
So I'm going to point myself out before you point me out.
All right. Go ahead, Mr. Gordon. What's the first thing we need for that?
Draw your circuit.
You're from the old school. You're smart. So we draw a circuit. So we have 5K, 5 Henry, and we have 100 microfarads. And here I have 20 volts, and I am closing the switch at T equals 0. I want an expression for the circuit current. So now that I have my circuit, where do I go from here? So God, you think you can only tell me to draw a circuit and God? Where do I go from here?
Sorry, sir, I'm having some poor connection. You know.
All right, Mr. Brian, step forward.
You can find 2 parameters omega. Hello?
Why? Why do I want omega? Oh, that can help Mr. Gordon.
Repeat.
Oh, how is that going to help us?
Sir, I'm going off a similar question.
Oh, yeah, SWAT?
No, man, with SWAT, man. No SWAT.
What do you mean similar question? Look at the question before you. I don't want to hear about no similar question.
All right. So what we do after that?
I see why you were doing what you suggested. Why were you doing that? All right, cool. In the interest of time, Mr. Brian, tell me the approach. It's 2:21 and we have a far way to go.
All right, sir. So first things first, you want alpha.
Why?
Sir?
Why?
Do you want?
Yeah, why do I want these things?
Because when you're dealing with this RLC circuit, the form of current is gonna the current expression is gonna take into consideration both alpha and beta.
Alpha and omega, not beta.
Sorry, alpha and omega.
Okay. So it means therefore that we need to compare alpha and omega. That's all I was asking, Mr. God. Why you want omega?
Okay,
Right?
sir.
So you needed to find alpha and omega in order to determine the form of the current expression. So alpha, Mr. Brian?
Yes, sir. Is equal to R over 2L.
That's 500.
500.
500.
And omega?
1 over root LC.
That is
44.72.
44.71.
Yeah.
All right, I'm with Mr. Brian now, Mr. God.
All right, yeah, no problem.
All right. So obviously alpha is greater than omega.
So I mean, this is omega.
Yeah, we have a problem. You know, I'm going to change these letters. But anyway, carry on.
Why, sir?
I don't like how it sounds. But so the current then, what's the form in which the current, for the current?
It would be AE to the minus alpha plus beta T, doing it like that. Plus B E to the minus alpha minus beta T.
Ms. Brown, thank you, Mr. Brown. Ms. Brown, back to you. What is beta equal to? She left the room. All right. So she has left us. Okay. Let's go down the line again. Mr. Jones.
Yes, sir.
What is beta equal to?
Sir, beta is equal to the square root of alpha square minus omega square, which is 498.
Background is nice, man. Are you working in that nice? All right, so 498. So add and subtract from, so I is equal to AE to the Jones?
Sir, it'll be AE to the minus 2t plus B E to the minus 99998t.
998.
Yes, sir.
Are you using two devices?
No, sir.
Or you're in the same space with somebody else?
Yes, sir. I'm at school at the moment now.
Oh, okay. Smart chat. All right. Thank you, Mr. Jones. So going back down the line again, Sir Sayers, boundary conditions. Dixon, boundary conditions. All right, back to you, Ms. Hanson.
Yes, sir.
Boundary conditions. What do we say?
Oh, for that circuit?
Yes, ma'am.
Oh, all right. Well, the fact that the alpha is greater than omega.
Oh, but we deal with that already. So we are now at the expression for the current, but we are trying to find the constants. So I'm asking, what are the boundary conditions?
Oh, like the formula sine, beta, cos.
Well, you know, read sine. Well, we had read. Well, you weren't paying attention. Where were you?
P is equal to 0.
Hanson, come. Boundary condition.
So I got distracted for a second. So.
So in other words, you weren't paying attention. Ms. Richards.
Yes, sir.
Boundary conditions, please.
Would it be t is equal to 0 and I is equal to 0?
So at t equals 0, I is equal to 0. Thank you, Miss. So implication then, Miss Richards. So 0 is equal to?
A plus B. Then you're going to say that A is equal to negative B.
A plus B, which implies that A is equal to minus B. All right. So we can, well, there's no real benefit to rewriting the current expression. We'll just move on. So the next condition that you test, Ms. Richards, so we have test the current. What next do we test?
The voltage.
All right, so give me the voltage expression.
So it would be VR plus voltage across the resistor plus the voltage across the inductor plus the voltage across the capacitor.
Can you speak up? You're very low.
Sorry, I think it's the rain. You hear me any clearer?
You're loud though.
All right. So that is equal to 20 volts.
All right. Okay, so what's VR equal to?
VR will be equal to 0.
And what's VC equal to?
VC would be equal to the Q over C.
Because you're told that Q, that C had a charge of 450. Beautiful. Beautiful, I like this. So we have 450, 10 to the minus 6 over C, which is 100, 10 to the minus 6, so that gives us 4.5 volts. And of course, VL.
That would be L didt.
So L didt would be equal to?
20 volts minus 4.5 volts, which would be equal to 15.5 volts.
All right, so didt
would be equal to the 15.5 divided by L, which would be equal to 15.5 divided by 5, which would be equal to 3.1.
You did the question beforehand.
Yes, sir.
Ms. Richards?
Yes, sir.
Did you do the question beforehand?
Yes, sir. This one, I did this one.
Okay, good. All right. So we find DDT. All right. DDT of, yeah, all right. Let me not cross pages. It's a little messy. Oops. We're finding DDT of A e to the minus 2t minus AE to the minus 998T. Okay, so Beckford, finish up this one.
All right, so the idea to differentiate that here, I get minus 2a to the minus 2t.
Minus 2a minus what?
Minus 2a e to the minus 2t plus 998a e to the minus 998t.
Thank you, sir. And at t equals 0, we know that. So give me the expression now.
At t equals 0, you have minus 2a plus 998a equals 0. Or equal 3.1. So much.
Pardon?
I calculate is well.
So A is equal to 3.1 over 996. Yes?
3.11 times 10 to the minus 3.
Okay, so it means that I is equal to 3.11 e to the minus 2t minus e to the minus 998t milliamperes. And that's it. So I have gone through all the quote-unquote subheadings on the transients. I've looked at all the possibilities. Do you have any questions?
Not at the moment, sir.
Okay, no, sir.
Really just practice and review, sir.
That's from day one, eh?
Yes, sir.
That never changes you. All right, so I'm gonna give you some work to do. Okay. I'm gonna give you some work to do. Let me share this screen. Why am I not seeing this? Oh, okay. So this really is our next topic. Where am I? Okay, so we now need to look at resonance due to harmonics. It's now 24 minutes to 3, but I'm going to just go through this, but there's a more in-depth lecture on this in, on YouTube, okay? So you can access that when you feel like. But I'm not going to go through this again. It's quite a simple topic. Usually I take an hour or so with it. But what we want to do is just to go back to some of the things that we spoke about in Networks 1. And you'll have a little practice with this in your project. All right, so we have here a triangular waveform, and we have our square wave, and we know that these are made up of component sine waves. Yes, we call them harmonics. And these harmonics, is a fancy name, but all it means is that you have component waveforms which have frequencies which are exact multiples of the fundamental. Right? That definition we already know. We're quite comfortable with that, I hope. We know about a period function being periodic, means that it is repeated for each of its periodic times. Yes, it's the exact replica of the waveform is repeated after that interval t. Okay, so these are things that we would have done, but this isn't really our focus. All right. We know about the fundamental. Yes, that's that large waveform which has the same frequency as the wave that we are analyzing. And we know that that's the fundamental. And of course, in this instance, here we are showing it having the same frequency. Of course, if it has the same frequency, it means that the periodic time would be the same, yes, as the wave being analyzed, yes. And then we also have our harmonics. So we have our third or fifth, and in this case, seventh harmonic. And of course, if we continue with in ninth, and as you can see, this is building out to be a square wave. So we have gone through all of this already, something that you're quite familiar with, okay? But today, what we really want to be talking about is the impact of some of these harmonics on circuit operation. So within our complex wave, as we said before, if we have that complex wave supplying a circuit with a combination of passive elements, you and I know that depending on the value of these reactive elements, that we can end up with resonance occurring. Because, that resonant frequency is dependent on L and C. But it may not resonate at the fundamental. It may resonate at a harmonic, which is what we're going to be looking at. Yes? So we have our voltage producing a corresponding current. Yes? And each of the coefficients. So I1 would be equal to V1 over Z1. I2 be equal to V2M over Z2, etc., etc. All right? Am I saying anything that you're unfamiliar with? Because everything I've said comes directly from Networks 1. All right? Now, as I mentioned just now, there is the possibility of resonance occurring, given that I shouldn't put it that way. The resonance occurring is not very likely, right? In terms of an industrial setting, okay? And that is at the power frequency. Good? However, when you have a non-sinusoidal, because you are now exposing those same reactive elements to a myriad of frequencies, that possibility now increases. So let me say that again. When I have a pure sinusoid, I mean, you know, we operate at 50 hertz. Nice sine wave. Given the values of inductance and capacitance that you will come across in the industry, you're not likely going to see resonance occurring. However, when we're dealing with non-sinusoidals, yes? Or in other words, when we're dealing with complex waves, and these, by the way, students, do occur in industry, yes? The possibility of resonance occurring at one of these harmonics is then increased. So it may not resonate at 50 hertz, but it may resonate at 150. Now, I'm not using 150 hertz in my system, but the fact that I now have a square wave being produced, that square wave, as we have just shown, will have a fundamental at our power frequency, which is 50. But it also has a third harmonic, which is 150. And it has a fifth harmonic, which is 250, etc., etc., etc. So because you now have these additional frequencies, the possibility of resonance increases. That's all we are saying here. Now, what do we know about resonance? We know that at resonance, you have the maximum amplitude for your current, series resonance, that is, yes? And this is as a result of your impedance now becoming a minimum. We know all the other things in terms of you have purely active power, because of course the current and the voltage at this particular juncture would then be in phase. So all of those stuff that we learned from Networks 1, you know, now becomes a part of the mix. Right? What this means, therefore, is that the possibility exists that the current magnitude, because if you remember, we looked at this, yes? We looked at these amplitudes for our currents. And we said that they were equal to the voltage divided by the impedance. But if the resonance is occurring, let's say at the third harmonic, the possibility exists that I3M may be larger than I1M, because you are now going to be, although your V3M is smaller than your V1M, because you know your harmonic amplitude is going to be smaller. But at that third harmonic, because you run the possibility of resonance, if resonance occurs, then the resultant current may be larger than the current for the fundamental. That confuse you?
Yes, sir.
Let me give it another shot.
Run it again, please, sir.
Yes, sir.
Yes, sir.
Please
We're saying, let us assume that resonance occurs at the third harmonic. You and I know that from the voltage expression, the fundamental would have the largest amplitude. We know that. And as you look at the harmonics, the amplitude usually gets smaller. But we also know that the current amplitudes are dependent not only on V, but also on Z, the impedance. Yes? But
sir.
going back to what we already know about resonance. At resonance, XL equal XC. I'm talking about series resonance now. XL equal XC. And of course, they cancel each other and leave R. So the point we're making is that because the current is dependent on both V and Z, that although V is smaller at the third harmonic, because Z is now much smaller than Z3 is much smaller than Z1, then the current at the third harmonic can now be much larger than the current at the fundamental. Because there are two factors that's dictating the current: the voltage and the impedance. All right? And that's the main point we're trying to make here. So for the circuit shown, the condition for resonance at the fundamental, which we all know, is that XL equal XC, which is omega L is equal to 1 over omega C. This is what we know from whenever we did networks one. That's a condition for resonance if it is occurring at the fundamental. We're not going to get into the proof thing again. All I will say to you is that generally, at the fifth harmonic, 5 omega L equal 1 over 5 omega C. And the general statement is that at resonance, or if resonance occurs at the nth harmonic, then n omega L is equal to 1 over n omega C. And that's the key. That's all the theory you need. Well, Ms. Cameron, shocking. You can't believe something that easy in networks. I like your honesty.
Sorry, I'm not using networks, sir. Just wait until application comes into the mix.
Mr. Bryan, I would appreciate you keeping your negative thoughts to yourself. So that's it. So let's quickly take this question. We have 10 minutes. We will knock it off in 5. Take the question for me, please.
Okay, sir.
Still all right, sir. Hold on.
All righty. So we have an RLC circuit. Of course, we draw a circuit. That's a given. All right. We know the voltage, V equal, and there's the expression. And it says if the resistance, capacitance, find the fundamental frequency for resonance with the third harmonic. So we start out, and we said that for resonance at the third harmonic, yes, we know that 3 omega L is equal to 1 upon 3 omega c, which implies, well, we want f, right? So it means that omega squared is equal to 1 over 9 LC, or omega is equal to the square root of 1 over 9 LC. So work that out for me, please. Or, well, F would be equal to omega over 2 pi. So what is omega?
Sir, 1054.09.
1000?
54.09.
Everybody got that? Just double check and make sure Mr. Black not teach some of the decimal places for me.
No, sir, I'm not teaching that.
Yes.
Just check.
Yes, sir.
Which means that F is equal to, is divided by 2 pi.
167.7 hertz.
So that's
0.76 or 0.8.
Go again? 167 point?
Or 0.76 or 0.8.
176.
1764, sir.
All right, Mr. Black, you know, I figure with the whole calculator. But it look like Miss Hanson have the same predicament, but we will heal him, don't worry. So that's the fundamental frequency. Next, we are asked for, well, I'm out of time. Next, we are asked for the maximum value of the fundamental and third harmonic components of current. So in other words, what we want is Z at the third harmonic. I'll call that Z3, and you want Z1. Now quickly, what would Z3 be equal to? Anybody?
V over V over I.
What does Z3 be equal to?
2.
2, because it's resonating at Z3, at the third harmonic. So this would be 2 ohms. All right? So I3 would be equal to, so we look back at the voltage expression. What is I3? I3M. Come on, man, I only have 1 minute left. What is I3M? What is V3M?
5 amps.
What is V3M?
10
volts.
So I3M is 10 over 2, which gives us 5 amperes. All right. Now for Z1, we would have to now find, how do we find impedance? Square root of?
R squared plus X squared.
So we'll have to find that. Because remember, the resonance is only occurring at the third harmonic, eh? So you'll find XL and XC. Square them, find the difference, find the square, add to R squared, find the square root. And then you divide the fundamental, which is 400 over Z1. All right. And we have a class at 3. But just, all right, tell you what. Yeah, so do that one. Find Z1. While you do that, I'll just take the register and then we can, I'll post the other question in Schoology, which I want you all to do, all right? And then you can, we can enter the discussion forum on that if you are having challenges with it, okay? So I will not be here after 3. Neither will I. No, I have to be fair. I'll be here tomorrow evening at 6. So the few who normally turn up, then I'll see you then.
Excuse me, sir. So this video will be posted, right?
No.
Different video,
It's not a tutorial, sir. It's going to be posted. As yes, sir.
Sir, Z1 will be 4,216.372.
Okay, so divide 400 by that, you get what? Less than 1. Good point.
Sir, I got 94.86 milliamp for the.
All right. And that's the point we're trying to make. The current at the third harmonic, even though it had an amplitude of only 10 volts, resulted in 5 amperes. But for the fundamental with a voltage of 400 volts, you end up getting less than a milliamp. No, that's not. Getting less than an amp. Sorry. Everybody with me?
Yes, sir.
All right. So, I know it is now 3 o'clock. Tell you what, write that off while you answer your name for me. Atkinson. Beckford is here. Bigger staff was not here. Black is here. Black is here. Bora is here. Brown left. Brian late. Cameron is here. Renee is here. Colwood is still here?
Yes, sir. Present.
Dixon's here. Peter John Facey was absent. Garden came late. Gray absent. Hanson here. Haynes, Hodges. Humphrey? Marley also absent. Jones. Luton? Absent. Trey Marshall absent. Bean McCleary? Absent. McFarlane absent. Morgan. Linval Morgan?
Present, sir.
Oh, no, don't recall seeing you. You came late?
No, sir. I was here from early.
Oh, I skipped you. I skipped you then.
You called on.
I called on you.
Yes, sir. You called on me, and while I was at the question, was at that time I lose connection from.
Okay. Morrison, Parker. Daniel?
Yes, sir.
Okay, Powell Richards. Joel Richards? Don't remember seeing you. Romain is here. Sawyer Stevenson? Absent. Stuart Swaby? Don't recall seeing you. Watson? Michael Watson? All right, and Patrick and Travis were here. All right, that's it. As soon as you are finished taking the question, you can log off.
I never heard my name.
Sir, so the calculator being radiant for this topic.
Huh?
Yes.
So the calculator being radiant when we're working on question like this.
Yeah, it happens to do it now.
Sir, I never heard my name, sir.
Who is that?
Oh.
Let me know, Mark, man.
Okay.
I want to call those who I'm not sure of. All right, so as I said, you can log off as soon as you're through.
All right, so have a good one.
Take care.
All right, take care.